Hello, everyone. Welcome to this free webinar presented by WePast. I'm your moderator, Christina Ruiz. During the webinar, feel free to use the chat to ask your questions and discuss the topic. We will take time after the presentation during the Q&A to answer them. Throughout the webinar, we will stop the presentation to review. Look for the multiple choice review questions, which you'll be able to answer in the polls section. Go ahead and respond to these questions as they come up. You will have less than a minute to answer each one. This and other recorded webinars are available to WePass subscribers 24 hours a day, 7 days a week. You can register through wepass.com to become a subscriber. Today's webinar panel is on lessons learned from anthropomorphic phantom audits, presented by Paige Taylor, Senior Medical Physicist, Mallory Glenn, Graduate Research Assistant, and Sharbaka Edward, Graduate Research Assistant from the University of Texas MD Anderson Cancer Center. Thank you all for joining us. I'll turn it over to Paige.
Great, thanks for the introduction, Christina. We're going to be talking to you all today about lessons learned from our anthropomorphic phantom audits. I'm excited to be presenting this. I used WePast as a resource when I was studying for the ABR and find it to be really, really useful. So I hope you all learned something from our presentation today and looking forward to it. As Christina mentioned, I'm a physicist at the IROC Houston QA Center. We're based out of MD Anderson Cancer Center. For anyone who's not familiar with IROC's mission, our goal is to provide integrated radiation oncology and diagnostic imaging quality control programs. And we do this to support NCI's clinical trials to assure high quality data for clinical trial patients. IROC Houston services involve a lot of different activities. One of those is our site qualification. So these are kind of some baseline steps that institutions go through to become clinical trial participants. That includes things like a facility questionnaire, ongoing QA, and our baseline proton approval. We also help with clinical trial design and support. So we review clinical trials as they're being written and decide what kind of credentialing steps go in them and what kind of patient data analysis will occur. The third piece of our services is what we'll be focusing on today, and that's credentialing. Credentialing covers a lot of different areas, so specific protocols will have credentialing steps to participate, and that might include a phantom irradiation, IGRT analysis, a knowledge assessment, or benchmark cases. And we'll be talking about phantoms today. IROC also does data management and case review for clinical trials as well. So to kind of get a feel for who our audience is today, I'd love to know how many of you have irradiated a phantom before, whether you've done it yourself or maybe seen another physicist in your clinic irradiate a phantom.
All right, great. So this is up in the polls section. So everyone, if you could just go ahead and answer this question. And also, if you have any questions for Paige or any of the other presenters, you can do so in the chat. You can post those questions and we'll be going over them during the Q&A. All right, it looks like a lot of folks are familiar with this.
This is great. So this will be really helpful as we go through. Most of you will probably be familiar with the general process, but I'll describe our phantom family and the dosimeters we use a little more in depth. So here I have our 6 photon phantoms that we provide. These cover everything from head and neck type disease site to thoracic. We have spine, liver, prostate, and an SRS brain. We also have analogous phantoms for proton therapy, but today we're just going to be focusing on photon phantoms, and this is more likely to come up on the boards than proton phantoms. All of these phantoms we provide for clinical trial purposes, so a lot of these are used for credentialing for specific protocols, but we also provide these phantoms for a fee as well. So if an institution gets a new SRS machine that they want to test, they can request the SRS phantom for fee to test out their system. The data that we'll present to you today is both from our NCI clinical trial irradiations as well as our for fee phantom irradiations. All of our phantoms contain thermoluminescent dosimeters, or TLD, as well as radiochromic film. And these are used for absolute and relative dose comparison with the treatment plan. So on the left, I have one of our liver phantom inserts that's been unsandwiched. So you can see the targets are made of solid water here, and those hold TLD capsules. And then you can see on the right, we have an image of one of our brain phantom inserts, and you can see that radiochromic film has been darkened by the irradiation area. A little overview of the TLD we use. Thermoluminescent dosimeters are made of crystals. At IROC, we use lithium fluoride TLD 100 crystals. These can come in solid form or ground up. Typically at IROC, we use powder form that's condensed into capsules. When TLD is exposed to ionizing radiation, electrons in the crystal jump into electron traps. When the TLD is then exposed to heat, electrons are bumped from their excited state and emit photons. And the number of photons that are emitted can be captured by a photomultiplier tube, and the amount of captured light correlates to the dose that is delivered. So a little review question: what causes TLD to emit photons?
Okay, great. This question is up in the polls section. So for those of you who are with us here today, please go ahead and answer that question live. It'll be up on the right-hand side of this window. We'll give everyone just a moment to answer this question. And after you submit your question answer, you can, if you'd like, ask a question in the chat for our presenters, and we can go over that at the end during the Q&A portion. Okay, looks like the answers are still rolling in. We'll give everyone just a few more moments. All right, Paige, I think we can go over the answer.
Great. So it looks like most of you got this correct. Our TLD emit photons when exposed to heat. We also use optically stimulated luminescent detectors at IROC. These release photons when exposed to light, but the TLD, we get that signal from exposing them to heat. A little bit more about TLD. So we use TLD for absolute dose measurements in the phantoms. The uncertainty in these measurements is about 1.5%, so they're pretty accurate. Some of the advantages of TLD is that they store dose information. So when we're sending phantoms out to institutions, we need to be able to store that dose delivered so it can be sent back to IROC and read out here. So these are great for that purpose. They're also relatively small, and they have a high dynamic dose range, so we can irradiate the TLD up to pretty high doses. In our SRS phantom, for example, we go up to 30 gray in the delivery there. The TLD are also dose rate independent, so as newer machines become available that have higher dose rates, we can still use TLD for those measurements. If you're interested in learning a little bit more about IROC's initial characterization of TLD, I've listed an article from the Red Journal here that you can check out by Kirby. As I mentioned, we also use radiochromic film in our phantoms. Radiochromic film uses a leukodye that changes color when exposed to ionizing radiation. And that change in color can be correlated to the dose that was delivered through the optical density. I've listed a couple task groups here that talk about the use of radiochromic and radiographic film. One advantage of radiochromic film is that it gives us really great spatial dose information. So we use film to get that dose distribution from the phantoms. Typically, we have 2 to 3 films in a phantom, and so that will cover 2 to 3 planes within the phantom. So maybe sagittal and coronal, or coronal and axial. There's no chemical processing required, which makes it really easy to read out when it gets back to IROC. But radiochromic film is not the best absolute dosimeter. So we find that even though the shape of the dose response curve is pretty accurate, that absolute dose isn't great over time. So what we typically do is we create an optical density to dose conversion curve that's used on the film, but then we scale the absolute dose on the film by our TLD values. The analysis that we perform on the phantoms is both a point dose comparison of the TLD dose with the treatment planning system dose predicted in the TLD region, as well as a gamma analysis that looks at the percent of pixels passing the gamma criteria. Most of you are probably familiar with gamma analysis, but the Low paper here from Medical Physics is a really great introduction to gamma analysis. Our phantoms, I've listed the criteria for the gamma analysis for each of them at the bottom, and you'll see that it's not the same for all phantoms. And that has a little bit to do with whether we have high dose gradients in the phantom, whether heterogeneities are present. So you'll see, for example, the lung phantom has the widest distance to agreement criteria with 5 millimeters. And that has to do with that high amounts of heterogeneity in the lung phantom. And then you can see phantoms like the spine and SRS, where we expect really tight, accurate placement. We have a tighter 3 millimeter criteria there and a tighter dose agreement with 5%. The phantom irradiations are an end-to-end test of an institution's treatment process. So we're testing everything from the imaging of the phantom to contouring, treatment planning, and treatment delivery. And what we're doing is comparing the institution's plan to their delivered dose. So typically with phantoms, we're not assessing the quality of the plan. We do have some planning metrics that we send with the instructions, so a certain PTV coverage or avoidance of OARs, but those typically aren't assessed on a pass-fail basis for the phantoms. So we're just looking at, did what you deliver match what you planned? I've listed our pass rates here for our 6 phantoms, and I'll highlight a few and some of the topics we'll be talking about through the rest of the presentation. So you can see our SRS phantom has the lowest pass rate currently, and we have quite a few irradiations in this sample. I'll be talking a little bit about some of the challenges with SRS irradiations, including small field dosimetry. The head and neck and spine phantom run into some similar problems as the SRS phantom, with challenges in modeling the beam and small fields. And lastly, the liver and lung sort of fall into their own category. Both of these phantoms are typically irradiated on a moving platform. And when we add motion into the phantom process, this is an extra challenge for institutions to meet. Shabbat will talk a little bit about the lung and the challenges of motion management there. So to start, we'll focus a little bit on the SRS phantom. This is a solid phantom that contains a relatively small spherical brain target. The target has 2 TLD that we make absolute dose measurements with, and 2 films that are in the sagittal and coronal planes. So you can see an example of a treatment plan for this phantom on the bottom right. The biggest problem that we see with the SRS phantom is the ratio of absolute dose when we compare the TLD with the treatment planning system. So here I've shown the trend of the TLD to TPS dose ratio over time. And we see a significant improvement, which is great. In 2012, just after we introduced this phantom, the average TLD ratio was 0.97, meaning that we were measuring 3% lower than the treatment planning systems were predicting. At present, our average is about 0.99, so we're seeing an improvement there. So there are many causes for SRS phantom failures, and we'll touch on a few of them. One of them are the cone factors or output factors used for these small field irradiations. TRS 483 is a really great resource if you're looking to improve your accuracy of output factors on small fields. And modeling can be a separate issue here. So if you think of like a typical LINAC, a lot of institutions might just have one beam model for everything from a 2x2 field size up to a 40x40. But when we think about that, there are a lot of different physics issues going on with those large fields than with the small fields. So what might be necessary is to create a different beam model for your small fields. Or if you just have small fields, the accuracy of commissioning is really important there as well. We also see some errors in TMR in the TPS. We see some mistakes with the HU to electron density conversion curves, and Shabbat will talk about this a little bit with the lung as well. Sometimes there's incorrect reference specification in the TPS, so dose to muscle or dose to water, or an extra 1% error introduced there. And sometimes there's an incorrect manual adjustment of output factors. What's really important to keep in mind with these SRS phantoms and with small fields is that you need to be using the right dosimeter when you're calibrating or commissioning your small fields. So we want to make sure that the dosimeter is an appropriate size for those small fields and that you aren't having problems with partial volume averaging. It's best to follow guidelines like TRS 483 and AAPM guidelines to minimize errors. So we're going to be talking about some different phantom themes today. There are lots of challenges in phantom irradiations that include our SRS output, small field modeling, challenges with motion management, and multiple targets. Mallory and Shabbat will expand on each of these topics. And the good news is that the IROC feedback that's provided to institutions and to all of you today can help improve phantom results. So Mallory will show you that we're seeing some improvements, for example, with the head and neck phantom. And the more we can make the community aware of issues that we see, the more we'll see improvements.
All right, so I guess I'll take it over from here. Hello, everyone. I'm Mallory Glenn. Can you hear me? Okay, thank you. I'm Mallory Glenn. I'm a PhD candidate here at MD Anderson doing my dissertation work here with IROC Houston. And over the past few years, we've been looking at ways in which we can improve the identification and resolution of errors seen previously in our head and neck phantom. And so I'm very happy to share what we've learned so far. To get you started, here's a quick primer on the head and neck phantom. As you can see on the right-hand side of the screen, the head and neck phantom, it's made of a high-impact polystyrene in order to mimic tissue-equivalent materials. It includes 2 solid water targets, as you can see with the insert, as well as acrylic for the organ at risk, here mimicking a spinal cord. The head and neck phantom simulates a nasopharyngeal lesion with nodal involvement, and so you can see there are 2 PTVs that have to be treated simultaneously while avoiding the organ at risk. And this in itself presents a few challenges in the way that you do the treatment planning. But it's good for our case because it's able to best evaluate IMRT practice as a whole. And as Paige mentioned previously, our acceptance criteria for the head and neck phantom is 7% for a dose agreement, as well as a 4 millimeter distance to agreement when doing gamma analysis. So the head and neck phantom has basically been a workhorse for the IROC suite of phantoms, and it's been used in clinical trial credentialing since 2001. Over time, we've actually gotten a whole lot better as a community in being able to perform accurate IMRT irradiation. Back in 2001, the pass rate for the phantom was only at 66%, and now we're pushing 90% and even beyond in modern years. And as you can see, thanks to the interfacing between IROC and the general radiotherapy community, lots of good advancement and improvements have been made with regards to IMRT performance. But there still remain several different challenges in maximizing its potential accuracy. And so as of right now, the current pass rate is approximately 90%, which is, for all intensive looking historically, fantastic. But if you consider the fact that IROC ships out the Phantom at least a couple hundred times a year, that's still too substantial a number of institutions showing concerning results. And so the question then becomes, why are there issues in the way that we do our radiations, and how can we improve this process? And something that Paige alluded to that adds an interesting challenge into the mix is the fact that the Phantoms provide an end-to-end assessment of the treatment delivery process. That is that IROC is pretty much blind to the process anywhere between shipping and then receiving the Phantom back. In addition, it becomes really tricky to discern where errors can occur in the treatment delivery process because there are so many different potential sources of error. And on the screen are listed just a few, including, miscalibration of your LINAC, daily output variations, issues in doing the setup or the localization, or just completely missing the target, delivery condition errors like are couch-top rails accounted for in the treatment plan or not, and are they present at the day of delivery, issues in your commissioning data if you're using the wrong dosimeter, the TPS modeling, so basically the input parameters used to mathematically represent the physical characteristics of the LINAC, as well as the algorithmic limitations, which you could see like inhomogeneity corrections if you're using difference between AAA or Acuros XB and Eclipse. And I'll say for the last one, that's not typically the case for the head and neck because it is a very homogeneous Phantom. But to get you guys started, I actually want to kind of give you a preemptive question, say, what do you think is the most probable cause of error in static Phantoms? And I preface static because we're looking at a head and neck. This is probably the best patient case possible. So you can go ahead and answer the question on your screen.
Okay, great. Yes, this question is up for those of you who just joined us, and you can go ahead and answer it in the polls section. We'll give everyone just less than a minute to answer this. And I see we do have some questions for the Q&A, so that's great. We're glad that you're all weighing in for that portion of the presentation. And if anyone else has any questions you'd like to ask any of our presenters, please go ahead and do that in the chat before we wrap up the presentation. So let's see, we're getting a lot of answers here, Mallory.
All right, fantastic. Well, then I'll go ahead and move on. So I think a few of you guys are going to actually be pretty surprised. The biggest issue that we see in static Phantoms is actually the baseline modeling of the photon beams. If you're really interested in learning more about how we were able to figure this out, I've got a really great paper to look at by Kearns et al. On the process we use to differentiate modeling errors from other errors at IROC. And so I'm going to talk a little bit more about where in the treatment planning we can actually go wrong here in this talk, so stay tuned. For this talk, I will actually talk on setup errors as well, because those do actually occur a fair number. But I really want to get down to the point on the beam modeling and see how we can actually improve this process as a whole. And so, let's see. And so in order to understand what's happening with these Phantoms, we sought to categorize the cases in looking back on old failing Phantoms to see what we could discover. And we were able to generate 4 different overarching categorical descriptions, which we called our systematic dose errors, our setup errors, localized dose errors, or global errors, which encompass pretty much if there were multiple error modes present in these Phantom cases. I'll touch on the first 2 as I've described previously. And so for setup errors in recent work, these accounted for about 13% of our failing cases, or if you consider that 90% of our cases pass, this is about 1% of cases overall. On the right-hand side of the screen, you can see dose profiles taken through the primary and secondary PTVs for a target. And you see very clearly that what was measured in blue versus what was predicted by the TPS in pink, there's about a systematic shift of about 4 millimeters, and this makes it fall outside of our criteria. Fortunately, and in an ideal case, these sort of these radiations will be performed by the same staff as you would in clinical practice. That is the the radiation therapy technologist will be the one doing the setup for the CT as well as the setup for delivery. And so we expect that these are not supposed to be a significant issue in clinical practice because you have the preferred staff doing the preferred objectives during delivery. Onto our next set of errors, we have the dosimetric ones. These are overwhelmingly the case when we see a failing phantom. And in fact, you can tell by the profile shown on the right-hand side of the screen, it has the profile shown has the right shape, it's in the right location, it's simply just the wrong magnitude of dose delivered. And in fact, in half of all of our failing phantom cases for the head and neck, these were shown to be systematically low, or to say that the treatment planning system overestimated the dose that was delivered to the target. And we know that this is a systematic issue because we've actually done statistical analysis to see and found out that the doses between the primary and secondary PTV, all of these were correlated with one another. So we know that it's not just offset in one PTV versus another, it's the wrong dose everywhere. And here on the screen, you can see that the difference is about 8%. So that's very much outside of criteria and certainly outside of what anyone would want for clinical practice. And so this brings us to the idea of our treatment planning system modeling errors. Now, we know that a lot of possibilities exist for where dosimetric errors can come from, but we also know that the TPS has a very large potential for impact. If you want to know a little bit more about different patterns and failures to identify these sorts of errors, I recommend the two papers I've shown here, Molyneux et al., shown in MedPhys, and Nelms et al. From 2013. From the work that I'd shown previously as an answer to our question, from Kearns et al. From the Red Journal, we found that a significant majority of our failing phantoms were associated with considerable calculation errors in the treatment planning system. And in this work, what we were able to determine is we used what we considered our average B model based on a whole bunch of different site visit data. And this average B model, for most of the failing cases, outperformed the institution's traditionally commissioned TPS in better predicting the dose delivered to the TLDs. And again, a strong majority of these showed that the TPS overestimated the dose when compared to the TLD in film. And so this then begs the question, where are these treatment planning system errors coming from? There are a couple different interesting possibilities. First, we have, is there inaccurate commissioning dosimetry data? That is, are people improperly measuring their profiles, PDDs, and output factors? As Paige alluded, there is an existing error shown in the way that people do small field dosimetry, and that can be issues of using the wrong detector size, right? Especially if you get down to small fields, you have to be able to adjust the size of the ion chamber to accurately capture that data. And if you are very interested, IROC has also put out a standard data set for small field output factors. So in case you find yourself commissioning small fields, you can actually refer to this article to see if you have a good feel for whether or not the values that you've measured are appropriate. Another area where treatment planning system errors come from can be just from the beam modeling itself, or the way that parameters are tuned to best approximate the photon fluence. And so one of the challenges that comes with this is that current TPS guidance documentation is actually pretty general in implementation. If you take a moment and read through the Medical Physics Practice Guideline 5A, it has a whole bunch of different credentialing tests for your treatment planning system. And this typically involves different field sizes, looking at different outputs. But the problem comes in understanding how people are actually modeling the MLCs, the physical characteristics, and dosimetric characteristics therein. And so it can be very hard to identify which areas for which these errors do arise from. So something that we at IROC decided to do is we wanted to ask people how they were actually doing their beam modeling to see, is there agreement, is there disagreement, and how that may itself be related to our phantom performance. And so what we did, we took a survey starting from January 2018 through January of this year. and then had asked them, how are you doing your modeling of your MLCs, of the effective source size, and other typically non-dosimetric properties? And what we determined was that, in fact, for similar LINAC models, let's say for all institutions using 6MV on a variant trilogy unit with the standard 120 MLC, it was very interesting to see that users disagree on what values best represent the machine's physical characteristics, which is unusual because you would think that for a similar machine with a similar build, they should be using similar values to represent physical manifestations. And in fact, another trend that we had observed is that generally for the more parameters that were available to tune, say hello, Pinnacle users, there was actually less consensus on what values were most appropriate for the given machine type. And so the more you're able to fiddle with your model to get what you believe is the best representation, the more there was a likelihood in being disagreeing with your fellows in the radiotherapy community. And so over here, I wanted to show a histogram of some of the values provided to IROC for Eclipse, for the dosimetric leaf gap. Now, again, Varian provides documentation on how to measure the leaf gap, so it should be a physically measured value. And even with this, there's a large range of disagreement on how people actually identify the best value used for their model. You can see it actually appears quite Gaussian. We have a median value of about 0.17 centimeters, which seems physically reasonable. But then you also have these guys out here on the edges. And this sort of raises an interesting question, like, okay, if these are outside of what institutions classically use for their models, how could these values then affect our planned performance? And what we've been able to show is that there is indeed some interesting work to be found there. And other questions that come about when you think about the modeling is that whether or not does the complexity make a difference in our phantom performance? You think more modulation means a higher dependence on the accuracy, or rather the uncertainty of the model itself. And interestingly enough, we've actually found that complexity metrics were not very predictive of our phantom results, but in fact that other factors can still contribute to the degradation of our plan accuracy. And again, all of this points back to the fact that it comes down to making sure that the beam model commissioning is done with the utmost care possible. And this especially holds true, like we've been saying about the small fields. And we know for a fact, based on previous works, the MLC modeling itself is very sensitive. So much more care needs to be taken when adopting the most appropriate values for use, especially with IMRT and VMAT. And so with that, my big takeaway message is that beam modeling is a challenging process. It has a lot of high potential for errors, especially these sort of errors can have a high clinical impact because the treatment planning system is what you use for every patient, for every machine. And so understanding the utility and both the effects of modeling parameters can help us ensure more accurate dosimetry. And so with that, if anyone has any burning questions or is very curious to learn more about how we've come to these sort of conclusions and the ongoing work that we're doing, I will happily refer you to these references I have here on the screen. And so with that, I'll turn it over to Sharbaka.
Thank you, Mallory. Can you hear me? Good. Hi, everyone. My name is Shabbat Edward, and I am a third-year graduate student, and I am currently working on my dissertation, or my PhD project, rather, at IROC Houston at MD Anderson. And so today I'm going to be talking to you a little about the work that I have done over this past couple years on the IROC lung and spine phantoms. So our lung and spine phantom irradiations are both done using the thorax phantom, and you can see this phantom here on the left. We have the thorax phantom sitting next to the cork insert that is made to mimic lung tissue. And on the right, we see a cross-sectional image of this phantom where we can see the lung target sitting in the middle of the cork tissue, which essentially simulates lung tissue and is very less dense than the tumor itself. The spine target structure is different. It consists of the tumor, which you can see sitting on the vertebral body, which houses the spinal cord. And so the actual tumor that's supposed to be irradiated is sitting less than 1 cm away from a very sensitive organ at risk, the spinal cord. And so this presents a different dose calculation challenge and different optimization challenges than the lung target. And so based on what site is being irradiated for this phantom, we would insert the appropriate target structure and send the phantom to the institution for irradiation. In addition, the lung phantom sits on a motion platform to simulate patient breathing, and I have a short video that we're going to try to show you here in a few seconds. And I think the video maybe flips 90 degrees, so yeah, just FYI. Christina, can you play that video, please? Okay. Okay, so I'm not sure if everyone had their sound on. You had to specifically go to turn it on. But there is also a sound that's associated with the phantom that lets you know that essentially your patient is still alive. And as we saw from the video, the phantom moves superior to inferior. It moves a total of 2 cm. And it also moves slightly anterior to posterior, about 5 millimeters in that direction. So institutions are instructed to deliver 6 grades with the TLD and film for these phantoms. And the criteria for a successful irradiation is seen here, plus or minus 7% for the TLDs and 5.3 gamma for the spine and 7.5 gamma for the lung. The failure rates that we have seen between 2012 and 2018 for the spine phantom is about 17%, and the failure rate for the moving lung phantom is 13%. And so in order to begin to reduce these numbers, like my colleagues have touched on, this is a very large percentage of people who are unable to successfully irradiate this phantom. So we want to reduce this rate. And first, we need to know what types of failures exist in these phantoms. And so this is what we set out to do with this work. So to evaluate this, we looked at all of the failing lung and spine phantoms between 2012 and 2018. And I sat down with Paige and a few other IROC physicists, and we went through each of these failing phantom reports in order to evaluate the dose profiles and the gamma analysis results. And for each of these cases, we determined why the phantom failed the radiation. And based on the various failure modes that we got for each of the cases, we created categories and then placed these phantoms into the appropriate failing category. So for the spine phantom, we had 4 major categories of failure. The first one, as seen on the left, was a systematic dose category. And in this pictured example, we have a systematic underdose, where you can see the measured dose profile in blue is lower than the planned treatment plan and system profile in pink. And so we have an underdosing of the PTV in this case. Our second category was the localization category. And this example pictured here is a superior-inferior localization error. And you can see the measured profile in blue, again, is shifted superior to the planned. The third category we had for the spine was a dose fall-off region error. And we can see specifically in the high dose gradient region between the PTV and the organ at risk, the spinal cord, we see that we have an overdosing of this entire region. And as we know, the spinal cord is a sensitive organ, and so this is a major concern. The last category for the spine phantom was an organ at risk overdose category. And again, here we can see on the right, the profiles line up almost perfectly in the PTV. And when we get to the low dose region in the spinal cord, we see an overdosing of this organ. So overall, for the spine results, we saw that 60%, the majority of all of our spine phantom failures, were due to systematic dose errors. And this is very much like the head and neck, another static, highly modulated phantom. And so we see that this is the major cause for concern with these types of phantoms. Our other three categories of failure, we saw an even split, about less than 15% for each of these categories. And so moving on to the lung phantom results. Again, we had 4 major categories for the lung failures. The first category we see here on the left is a systematic dose category. Pictured here is a systematic overdose, and you can see in the PTV region, there is an overdosing of the PTV by, I'd say that's about almost 1 gray. And the second category we had was a localization category. Pictured here is a superior-inferior localization error. And also we can see there's a major shift. The measured profile is shifted almost 2 or 2.5 cm inferior to the planned profile. The third category that we saw for the lung was a global error category. And this one, we put phantoms that failed egregiously. Like you can see that it's shifted, the shape is off, there is an underdosing issue, just something pretty much crazy went wrong with this phantom. And so, go back. And so that was our global error category. And our last category is a combination error category. In this, we had phantoms that contain 2 different types of errors, where each of these errors on their own would not be large enough to cause the phantom to fail, but because they both existed together, then we saw a failure of that phantom. And so in this case, pictured here, we have an AP localization error, and you can see it shifted slightly in the posterior direction. And also we have a slight underdosing of the PTV. And so these two working together cause that phantom to fail. And now we can go to our poll. So based on the results that we've seen with the head and neck that Mallory spoke about, and the lung that I just spoke about, now thinking about the spine, now thinking about the lung phantom, what do you think is the major cause of failure of these phantoms? Oh, the poll's already up.
Yes, the poll is up, and some folks have already started to answer, which is great. So we're just going to give everyone else just a few more moments here to answer this poll question before we turn in the answer. All right, I think we can go over the result now.
Okay. So remember that our head and neck and our spine phantoms were both static, highly modulated. The lung phantom, however, as we saw in the video, it moves. And so when you add this extra aspect, we have most of our lungs failing due to localization errors. And so I'm going to touch on that a little more in the subsequent slides. Okay, so for our lung phantoms, we saw 62% of all of them failing due to localization errors. And of that 62%, we had 50% of this localization error being in the direction of motion, which is superior, inferior, and the other 12% being in other directions, so anterior, posterior, or left, right. And like I just mentioned, this is a major a major reason for this is due to the fact that the phantom does move. And so we see a lot of motion management issues with this phantom. Our second most popular category for lung phantom failures was systematic dose errors. And looking at global errors, we only saw 2%, which makes sense because global errors essentially represent just a mistake or human error in the process. So looking a little more closely at motion management issues, we decided to look at the major category of failure, localization in the superior inferior direction. And you can see this highlighted. And we looked at them, we broke down the phantoms in this category by the different motion management techniques. So we had people who irradiated the phantom using free breathing or ITV. We had some who used the gating method, and we had some who used no motion at all. And I will touch on that in a little bit. And so we see that of all the people who used free breathing, we had 10% of all of our phantom failures being due to, or 10% of all people who used free breathing as a motion management technique failed due to localization errors in the superior inferior direction. So you can see 47 out of 466 total free breathing treatments between 2012 and 2018. Gating, we saw 16 people failing because of motion management out of 125 phantom irradiations for 13% failure rate. And whereas with static, only 1% failed in the direction of motion. And also we noticed that statistically there was no difference between using free breathing or gating techniques. And so you're equally likely to fail due to a localization error in the direction of motion if you use either of these treatment techniques. Now, looking at all failures overall, in the previous slide, I looked at failures in the direction of motion. Now I'm looking at just failures in all categories. We also saw that if you used gating or free breathing, you were more likely to fail the phantom overall. And so we saw an 18% failure rate for each of these motion management techniques for our phantoms between 2012 and 2018, whereas only 2% of all static phantom irradiations failed the treatment. And so you may be wondering, why do people even irradiate this phantom static? It's a lung, it moves because people breathe unless they're dead. And so you expect motion in your patients. Well, the lung target structure, like I mentioned a few slides ago, we have a tumor that sits in the middle of the cork material, which is a much less dense material than the tumor material itself. And so we can use this phantom in order to test inhomogeneity calculations. And so if someone wants to test their ability to calculate dose to a target in air, essentially, you could use this phantom for that purpose. Okay, so since our second most popular category for the lung failures was systematic dose errors, we were thinking that perhaps the majority of those who fell into that category were static phantoms. And so since they had no motion, then the only way they could fail was systematic dose errors. But we were wrong. Looking into the phantoms that fell under this category, we found that 80% of them actually did have motion when they irradiated the phantom. And most of that motion was free breathing or ITV. As you can see here, we only had about 7 static phantoms. And so these phantoms that failed due to dosimetric errors, there's actually an inherent dose calculation issue present here. And so we decided to look more at the algorithms that they use to calculate dose to these phantoms. And we found that 71% of all of those who failed due to systematic dose errors, they used either the AAA or convolution superposition algorithms. And it may be known that the Accurate, or abbreviation AXP algorithm, is specifically designed or tailored to heterogeneous targets. And so it has been recommended to use that algorithm for lung dose calculations. And so 71% of these people who use this, who failed due to this dose calculation error, did not use the Accurate algorithm. Another error that could be contributing to people failing due to dose calculation issues is the HE2 density calibration, or electron density curves. This graph shows data that we collected from institutions who irradiated the lung phantom. And you can see in the region near the lung tissue, you can see the different structures in the phantom represented here by the vertical lines. And near the lines that represent the lung tissue, we can see that some people are slightly off of the curve. You can see these points that are slightly lower than the normal. And so that could also be contributing to the way that they calculate those to the lung. Also, if you look to the high end, the high density end of this curve, we can see there are a lot of spurious points, or people that are off of the normal trajectory of the curve. And so that could be contributing to our spine dose calculation issues. And that is something that we will be exploring in the future. So in conclusion, overall for the spine phantom, like the head and neck, we saw mostly systematic dose errors present. And so these static, highly modulated IMRT treatments, the major cause for concern is systematic dose errors, or TPSB modeling, like Mallory mentioned a few minutes ago. For the lung phantom, we saw a different story. Most of the lung cases, or rather 50% of all lung failures, were due to localization errors in the direction of motion. And so this tells us that motion management is a big issue with this phantom, and it's something that needs to be improved upon. So all of this work has been written up and submitted as a manuscript, and hopefully will be published within the next month or so. And so if you're curious about learning more about this, you could look out for that soon. Also, I wanted to point out that the errors that we do see in these phantoms are clinically relevant because they're not due to human error or mistakes. Look at how small our global error category was. It was only 2% of all of the failures. And so these are errors that could also show up in the clinical process because they are errors that exist in the process of calculating and motion management and irradiating this phantom. They are errors that could show up again in patient cases. Also, IROC has a pretty loose criteria, like someone mentioned in the chat a few minutes ago. And even with this criteria, we're seeing such a large failure rate. And so there is even greater concern for the more strict clinical criteria. Are people even able to meet this criteria? That's of great concern to us. And essentially, all of this work is part of larger efforts at IROC to identify, quantify, and eventually rectify the errors that we see in institutional phantom irradiations. And with that, I'd like to thank you for your time.
Okay.
Questions now.
Great. Yes, we can move on to the Q&A. So I guess we'll have to be taking turns chiming in here. Our first question is, I know Paige answered some of these in the chat, but just for the sake of the recording, since those who will be seeing the webinar after the fact won't get to see the chat, I wanted to do these with the audio. So why is the RCF dose scaled based on the TLD dose? Why not ion chamber dose measured for the same plan or radiation?
Yeah, that's a great question. So since this is a remote audit, we have the challenge of only being able to use passive dosimeters. So ideally, we would love to have ion chamber measurements at the center of all of our phantom irradiations. But the physicists at IROC aren't physically going with the phantoms, so we use TLD instead. And one might ask why we don't ask the institution to do an ion chamber measurement. We really want this to be an independent test. So if we're asking the institution to do a measurement, then we aren't really verifying if they have an error with their ion chamber calibration or something like that. So to maintain independence, we use the TLD for this remote test. Great question.
Okay, thank you. Our next question is, for phantom radiation gamma analysis, do you use a low dose threshold, i.e. 10% of RX dose?
Typically, we don't use a low dose threshold. We've been developing this capability, but most of our ROIs that we use to do the gamma analysis are pretty closely cropped around the PTVs themselves. So we aren't including very much film region with low dose, but in the future, we would like to do some thresholding.
All right, our next question is, the centers that failed SRS Phantom, did they redo the test after correcting issues? What is the percent pass after corrections?
So for most of our phantom failures, typically the IROC Houston physicist who's in charge of that analysis calls the physicist who did the irradiation to kind of troubleshoot with them. So this happens with our SRS and all of our other phantoms. So we'll call and let them know, hey, we saw that the dose was low, or we saw that there was a shift in the setup, and try to give them some ideas of things that they can look into to improve. So after that happens, we offer that the institutions can repeat the phantom irradiation, and our pass rate for repeats is much higher. I don't have a number offhand with me for the SRS phantom, but we see that the repeat pass rate is much better than first-time irradiations.
All right, great. This is another question. Are there plans to tighten the pass criteria?
So this is something that we've looked at many times before. Our initial criteria is based on pilot studies for each of these phantoms. So typically we'll look at a 90% confidence interval, and we're keeping in mind the limitations of the dosimeters we're using. So TLD are accurate within plus or minus 1.5%. Our dosimetric precision for spatial accuracy on our film is about 1 millimeter. So we keep that in mind when we establish our criteria. We also have our criteria approved by the clinical trial groups. So when we have a new phantom, we'll go present our pilot data to the clinical trial groups and say, this is what we're proposing. And then there's a medical physics committee that votes on that criteria. So if we want to change our criteria, we need to go back to that committee and get their approval. We have looked at tightening the criteria on our phantoms. This pretty dramatically increases the failure rate for the phantoms. So for head and neck, for example, we've looked at 5%, 3 millimeters. Mallory, did you run that analysis? I can't remember. For tightening criteria.
Oh yeah, that was part of my paper.
So, we go from maybe a 90% pass rate to a 70% pass rate, or 65. So that presents a challenge because we're trying to get these institutions to participate in clinical trials. And if half the institutions can't participate, the trial groups aren't very happy about that. So we kind of have this balance between providing meaningful feedback to institutions and then trying to get institutions to participate in the trials.
And if I could just chime in real quick, if you're interested in knowing what sort of things happen when we've tried evaluating different pass rates, I actually published a paper back in 2016 examining credentialing criteria and poor performance characteristics. And in there is a table that shows how our pass rates could potentially change by looking at different criteria for evaluation.
Okay, great. Thank you so much, both of you, for answering that question. Our next question is, has IROC looked into providing gel-based dosimetry to provide a more comprehensive evaluation of the treated volume?
We have. So IROC had a pretty active research group that was working on this for several years. And we've done some phantom irradiations with gel dosimeters. For the most part, we found they just weren't as accurate and reproducible as our current system. It's nice to get that 3D dose information, but we're able to do sort of 3D dose analysis with our current film and TLD setup. So, so far, we haven't found a good enough system that we're willing to switch over. We also find that when you do a 3D gamma analysis, it's much less sensitive to errors. When you're doing 2D, those translational errors and setup are a little more obvious, whereas with 3D gamma, it covers up some of those mistakes. So we feel like we're getting a little better information from the 2D gamma that we're able to perform with the films.
All right, thank you. Our next question, I believe, is for Mallory. Regarding the dose profile through the HN targets, it was presented that it represents the systematic error of the TPS, if I understood correctly, but what is the probability that it could be the error in the film registration?
So this is an interesting question, and if I understand the question correctly, alluding back to what Paige described, is we actually, okay, you could also just say that. You would know the answer better than I. But since we register the film to the TLD measurements, a lot of the uncertainty surrounding the dose, the measured values for the dose would be within the TLD uncertainty of about 1.6%. But if we're talking about film registration in terms of like spatial registration, that uncertainty is about 0.35 millimeters. So very, very small.
Okay, thank you. Our next question is IROC looking at methods to investigate underlying reasons, individual failures? For example, for systematic dose phantom failure, you could send out your standard output OSL to specifically evaluate that aspect, or you could have a true beam customer irradiation of phantom using one of the generic machine QA plans that every true beam comes with, so it is standard. I think that's a question.
That's a great question. So we do send an output block with all of our phantom irradiation. So we're able to see if on the day of irradiation, the output of the machine was high or low. Typically, we will find, though, for a 10 by 10 irradiation, the output looks fine. But then when you get down to small fields or small segments, because of the difference in beam model, that's where we have errors introduced. For some institutions, we do provide, we have like a virtual visit program where we collect machine data and run it against IROC standard data. Mallory has also worked on an external beam validation program that she presented on. So if we're really not able to tease out where those errors are coming from, we have those types of tools that we can use to look and see if it looks like there's an error in the beam model.
Okay, thank you. Our next question, I think, is a follow-up. And similarly, the 8% dose error was attributed to the TPS beam modeling issue. However, there could be uncertainties with the film scaling based on TLD. Does IROC consider this type of issue?
So typically, if an institution is failing the film analysis, the gamma analysis, because the dose is high, they're also failing because the TLD is high. So those are separate criteria in the pass fail analysis. So if your TLD is 8% high, it doesn't matter what your gamma looks like, you're going to fail that phantom irradiation. As Mallory mentioned, and I think I mentioned, the accuracy of our TLD is about plus or minus 1.5%. So if the TLD is 5% high, but our gamma analysis goes up to 7%, then that film presumably should pass that analysis. So we don't have too many concerns about the TLD scaling there. We do know that film absolute dose is not as accurate as TLD, so we trust the TLD for that purpose.
Okay, thank you. We have a couple more questions here. Are there plans to include fiducials and IROC phantoms to help perform ETE testing on fiducial tracking delivery?
Yeah, great question. We have a couple phantoms, both our SRS and our lung phantom do have fiducials available. Not all of them have it, but we have a few of each of those phantoms with fiducials. We're constantly trying to adapt our phantoms for new technologies. So we've developed a couple MR compatible phantoms for new MR Linacs or ViewRay systems. We've developed proton phantoms, as I mentioned. So as new technologies come about, we try to adapt to that, particularly because these new technologies are often tested in clinical trial settings. So we want to make sure we can test those for clinical trial purposes.
Okay, great. Our next question, what kind of agreement did IROC get when they did this phantom measurement themselves at MD Anderson, an ideal situation?
That's a great question. So all of our phantoms typically go through a testing phase, a pilot study. Most of the phantoms have been a graduate student's master's project at some point. So I got my master's degree working on a proton brain phantom. So if you look online, there should be theses and publications about each of these phantoms being commissioned. I can give you some data for the head and neck phantom, for example. So typically what we'll do is we'll develop the phantom and then we'll do a series of irradiations to check for the accuracy and reproducibility. And that's all done by IROC in a very controlled setting. So for the head and neck phantom, the TLD doses were within 1.6% and the spatial accuracy was 0.35 millimeters. So these are well within our 7% 4 millimeter criteria for that head and neck phantom.
Okay, our next question is a follow-up to a previous question. MPPG5A has a great list of tests for diagnosing what is wrong with the TPS. This is in reference to the question on what to do if you fail IROC.
Yes, and actually, let me better clarify what I was stating when I say MPPG5A is a fantastic resource for determining the overall accuracy of the beam modeling you have in your system. But one of the tricks about it, and especially just because we work in a multi-vendor society, it's hard to determine parameter by parameter which values are the most appropriate for the adaptation of your beam model. Fortunately, I would like to come back to this and say that we're actually in the process of publishing our survey results, and those should be up within the next couple of months. And so we're hoping to use this data set as a tool to help the community better understand what values are, say, most widely adopted or the most appropriate for use.
Okay, thank you.
Also, sorry, let me go ahead and mention actually, we also already have the data available on the IROC website. You can find that under our reference values tab.
Okay, great. Thank you. This is our last question. What percentage of institutions that submit phantoms are interested in knowing if their own institution can pass, but not necessarily to participate in clinical trial?
That's a great question. So over the past few years, our percentage of for-fee phantoms has greatly increased. And I think right now we're at about 40% of our phantoms are for-fee. So that's just institutions wanting to double check a new machine or a new algorithm or something like that. And about 60% of the irradiations are for clinical trials.
Okay, great. Thank you so much for answering all those questions. And thank you again for presenting this webinar and for all of you for joining us for this free event hosted by WePast. If you're interested, the next webinar will be next week on valuable aspects of commissioning a Halcyon linear accelerator presented by Tucker J. Netherton on Thursday, October 10th at 6 p.m. Eastern. And don't forget that this and other recorded webinars are always available to WePass subscribers 24 hours a day, 7 days a week. So register through wepass.com to become a subscriber. And for update information about upcoming webinars, be sure to follow WePass on Facebook, Twitter, and YouTube. And thank you again for presenting this webinar. We'll see you next time.
Thank you.
Thank you guys so much.